Good afternoon. Let me just connect this. Those of you on YouTube can already hear me, but let's connect Teams. Good afternoon. Just let me know by way of a thumbs up. Can you hear me? And can you share my screen? Well, see. I don't know why I said it like that. Okay. Guys, can you hear me? Just a thumbs up or what? If you can hear me and if you can see my shared screen. Thank you, Ms. Nolutando. Okay. Today will be a relatively quick session. I think we'll be done in about half an hour. Okay. This has to deal with, or the session today has to deal with our inductance. Okay, RLC circuits. So inductance, we're doing inductance. I'm just looking at my question. Okay, there we go. Today we're doing inductance. Okay, it's chapter 32 in your prescribed textbook. Okay, and this is just question number 1. Now you don't have to worry about the question itself, uh, or the question number. Worry about the question itself. Let me just, okay, don't write this thing. Okay, there we go. This question asks us, okay, if we have a, and I'm just going to go right into it. You guys that are listening, just stop me if you don't understand anything or if you want to ask more questions. Okay, now I see a few people just joined. Welcome. I'm about to start. This won't be a long session. It's based on inductance. So, this question, the first question says, a series LC circuit contains a 100 millimeter, oh, no idea why I said millimeter, but inductance is denoted by an L. So it contains an inductor that is 100 millihenry and a capacitor with a capacitance of 36.0 millifarad. Okay, so we have an LC circuit, and they are all connected to a 12-volt battery. Okay. So a series LC circuit contains a 100 millihenry inductor, a 36 millifarad capacitor, and a 12-volt battery. Okay, and the question then is, the angular frequency of the electromagnetic oscillations in the circuit is. So they want us to calculate the angular frequency of the EM oscillations. Okay, so the angular frequency of the EM oscillations, if we are given that the inductance is 100 millihenry, the capacitance is 36 millifarad, and the voltage is 12 volt, and they are all connected in series. Okay, so they're all connected in series, and we have the inductor, a capacitor, and a voltmeter, or a voltage that is being supplied. Let me see. And they want the frequency of the electromagnetic oscillations. Okay, now there is one formula that allows you to calculate the angular frequency of an oscillation, of an EM oscillation in a LC circuit. And that formula is, it says that the angular frequency is equal to 1 over the square root of the inductance multiplied by the capacitance in that series circuit. Okay, this will allow you to calculate the angular frequency of this particular circuit. Okay, it's a simple formula, and those of you who just joined, we won't be here long, 25 to half an hour maximum. Okay, so now we have a formula to calculate the angular frequency. Let's plug in what we know. So the formula is that the angular frequency is equal to 1 over the square root of the inductance multiplied by the capacitance. So, what did we say was the inductance? They gave us that the inductance has an inductance of 100 millihenry. And if we plug in 100 millihenry, that is just zero point 0.1 Henry. Okay. Remember, I could have just said 100 times 10 to the negative 3 Henry. Okay. So zero point 0.1 Henry is the inductance. And then, of course, we must multiply that by the capacitance, which in this case is 36 microfarad. 36 microfarad. If we write 36 microfarad, yes, it's 36 microfarad. And if we divide that by 100, or rather 1,000, it should be 0,036. Okay, and that is in farads, of course. And thus, if you do this calculation, I'm going to show you at the bottom there on the calculator. I don't normally do this because to me it is kind of redundant. I know that you guys can do this on your own. So, but let me do this rather. So we have that the angular frequency is equal to, where is the bottom? There. So it is 1 over the square root of 0.1 multiplied by 0.036. And that gives us an angular frequency of 16.67 radians per second. Remember, we're calculating angular frequency radians per second. Or we can just write this as approximately 16.7. 16.7 radians per second. And let's check and see if any of our options there give us 16.7 radians per second. There we have one. If we check it, let's see if it's correct. There is a green check mark next to it, meaning it is indeed correct. Okay, so we've calculated the angular frequency. What you need to take away from this question is angular frequency of an LC circuit is related to the inductance and the capacitance via this formula. Okay, you need to know that formula. Okay. Question number 2. What does question number 2 require of us? What do we need to do? Okay. There it says that the correct answer is indeed 16.7 radians per second. Now here we have an actual switch. Okay. It's question number 2. Don't worry about the question numbering is there for me to keep track of it. Okay. So it says before the switch is closed in the figure. Okay, so at this point it is open. It's an open switch. There is an inductor there of 0.2 henries, and there is a 4 microfarad capacitor there. Okay. They tell us that before that switch is closed, the potential across the capacitor is 200 volts. Okay. So the potential across that capacitor here is 200 volts. At some instant after the switch is closed, so then they close the switch, and immediately after that switch is closed, the instantaneous current in that circuit is zero point 0.7 amperes. Okay, they ask us then, what's the energy in the capacitor at that instant when the current is zero point 0.7 amperes? What's the energy in that capacitor? Okay, now what formula do we require to calculate the energy of a capacitor? Remember, to calculate the energy of a capacitor, we use this formula. The energy of a capacitor is equal to a half times the capacitance. Let me just close this here. A half times the capacitance times the voltage squared. That's how you get the total energy. That's the total energy in a LC circuit. Okay, but we are not interested there in that problem left. So let's calculate. Let's see what they've been given. Well, what we've been given. We've been given that the capacitance is, what is the capacitance? It's 4 microfarads. Okay, so it's 4 times 10 to the negative 6 farad. That's the capacitance. Okay. Then we have that the voltage, the V initial, the initial voltage, the initial voltage. I'll just write VI. Much easier. So the initial voltage is 200 volts. And the instantaneous current, I'll say instant. The instantaneous current after the circuit is closed or the switch is closed is 0.7 amperes. I usually like to write out everything I've been given so I know immediately what I need to do. Okay, so first of all, we need to calculate the total energy. They want the energy in the capacitor at that instant. So first, let's calculate the total energy. Okay, let's calculate the total energy. E total will be equal to a half times C times V squared. Okay? That's a half times C, which is microfarad, 4 times 10 to the negative 6 farads, 4 microfarad, so 4 times 10 to the negative 6 farads, and then the voltage squared. That is the initial voltage, 200 volts, the initial voltage. That'll give you the total energy that was there before the switch was closed. So the total energy is then 80, or rather 8 times 10 to the negative 2 joules. Okay, you can just work that out by yourself. 200 squared, that is 20,000 or 40,000 rather, and then multiply that by 4 times 10 to the negative 6 and half it. This you can write as 80 millijoules. So the energy, the total initial energy is 80 millijoules. Now let's determine the energy in the capacitor. Okay, how do we determine the energy in the capacitor? Okay, we already have the total energy. Okay, what other device will take energy up? Okay, there are two things. There are uh, two components in this circuit. There is a capacitor and then there is an inductor, and the energy will be spread between the two of them. Okay, so the total energy, which we just calculated to be 80 millijoules, is equal to the energy provided by the inductor plus the energy of the capacitor. Okay, those two should give us the total energy. Now we know we just calculated the total energy between 80 millijoules. That's the total, 80 millijoules. Now the energy due to the conductor or the inductor rather is what? That is what we need to calculate. Okay. How do we calculate the energy of an inductor? Okay. So we need to calculate first of all the energy of an inductor. Let's do that on this side. Okay. Before I continue, let me first calculate the energy of an inductor. So EL, the energy of an inductor, is equal to a half, again, times the inductance, times the instantaneous current squared. Okay, so times the instantaneous current squared. So it will be a half times the inductance, which in this case is zero point 0.2 Henry, multiplied by the instantaneous current. They tell us it is 0.7 amperes. Then you square that, never forget to square. And that, ladies and gentlemen, should give you an answer of, and I'm going to write it in joules first, 0,049 joules. Or if you write it in millijoules like we did with the other one, it is just 49 millijoules. Okay, so now we have the energy that is from the inductor. So you have learned two formulas so far. Okay, how to calculate total energy and how to calculate the energy from an inductor. Okay, so let's see. Total energy, the formula for total energy is equal to a half CV squared, while the energy for an inductor is equal to a half Li squared, the instantaneous current squared. Okay, you need to know these two formulas for inductance. And then, of course, back to our old formula, the total energy is equal to the energy from the inductor plus the energy from the capacitor, which is what we want. We know that, or we calculated the total energy to be 80 millijoules. We just calculated the energy from the inductor to be 49 millijoules plus the energy from the capacitor, which we want. If you subtract these two, 49 millijoules from 80 joules, you'll get the energy of the capacitor, which in this case will be 80 minus 49, and that should be 31 millijoules. Okay, 31 millijoules. I hope everyone understood that, how we got to 80 or 31 millijoules. Okay, 31 millijoules. Let's go check if there is an option for 31 millijoules and whether that option is indeed correct. Okay, there is 31 millijoules. Let's check. The correct answer is 31 millijoules. Okay, so question number 3. Here we have a circuit. Okay, it has these various components. It has a voltage source, two switches, a point A and a point B. If it's at point A, the big circuit is closed. If it's at point B, the smaller circuit on the right end is closed. Okay, so they ask us, what is the current in the inductor at the instant the switch is thrown to position B? Okay, first let's work out when the switch is in position A. So when it's at position A, so the big circuit is completed, we need to work on part B first in this case. When the switch is in position A, for what value of R will the circuit have a time constant of 15 milliseconds? Okay, so for what value of R will it have a time constant of 15 milliseconds? Okay, so let's look at the circuit. It is now closed at A, so you can ignore the middle part. That's at B, that ends at B. You can ignore that for now because no current will be flowing there, technically. So, for what value of R, so for what value of the resistance will the time constant be 15 milliseconds? Okay. First, let's work out what is The time constant. Time constant we can calculate as equal to, time constant is equal to the inductance of that circuit divided by the equivalent resistance. That means basically the total resistance of that circuit. Okay? So the equivalent resistance. Now we have the time constant, we have the inductance, we want the equivalent resistance. Okay? So let's work out the equivalent resistance. So the equivalent resistance is equal to the inductance divided by the time constant. The inductance in that circuit is 5 millihenry, so 5 times 10 to the negative 3 Henry divided by the time constant, which they tell us is, if we have a time constant of 15 milliseconds. These questions are just swapped. This is supposed to be part A, the second part, and then the other one is supposed to be part B. 15 milliseconds. 15 times 10 to the negative 3 seconds. Okay, so Henry per second would then be an ohm. Okay, let's do that calculation. 5 divided by 5, let me just make sure that's milli, and that's also millihenry. So that should be, if I'm not mistaken, a third or 0.3 ohm. I just want to check before I make a horrible mistake. I just need to check here. I have a calculator up here. Clear. Okay. So I just want to check. That's 5. E. Clear. There's the functions. That's natural log. No, standard codes. Okay, let me just check. Len log. Let me see. Main. Should be around here. What do I usually use? Okay. Let me just do it this way. We can see that it's 3, 5. Remember, I just did this quickly. 10 to the negative 3 divided by 15, 10 to the negative 3. That is 45. Should be 5 divided by 15. And for some reason, that's 5 times 10 to the negative 3 over 15. Nope, that's wrong. Clear. I have no idea why I'm... Oh, here it is, exponent. Wonderful. 5 exponent negative 3 divided by 15 exponent negative 3 as well. Equals 0.3. Yep, so I was correct. So we have 0.3 here. Okay, 0.3 ohm should be the equivalent resistance. Okay, so we know 0.3 equivalent resistance is equal to zero point 0.3 ohm, but we also know that equivalent resistance, look at those two resistors there, okay? If you were to look at them, you'll see that they are in parallel, okay? So how do we calculate the resistance in parallel? We know that the equivalent resistance in parallel is 1 over RQ is equal to 1 over R1 plus 1 over R2. That's why you did this earlier on. And one has a resistance of R and one has a resistance of 450. And the total is zero point 0.3 ohm. The equivalent resistance is, or rather it should be 1 over zero point 0.3. 1 over zero point 0.3. Now 1 over zero point 0.3, that's 10 over 3 minus, so 1 over zero point 0.3 minus 1 over 450 will give us 1 over R. Okay? So 1 over 3, 1 over zero point 0.3 minus, and once you have that sum, that whole sum there, R therefore is equal to 1 over 1 over zero point 0.3 minus 1 over 450, which is equal to a value of 1290 ohm. So R has a value of 1290 ohm. Okay, let me just check my calculation here quickly. Yep. Okay, seems to be in order. 1290. Oh, wait, let me just check. They used microfarad. Is this microfarad? That is millihenry. They use, that's milliseconds. So they're both milli. Okay. So let me just check this calculation then. I think I might have used micro in one of them, but let's just see. This is how it should go. AC. So it is the inverse of zero point 0.3. Oh, there should not be 3, it should be 0.3. 1 divided by 450. And then 1 divided by zero point 0.3. 3 over 10, so 10 over 3. 10 divided by 3 is 3.33, so 3.33 minus the answer should be equal to 3.3 again. And if you find the inverse of that, zero point 0.3 cannot be. Let me see. Let me check. Somewhere there's a mistake. I think I did the correct thing, but let me check at the question. 5 millihenry, yes. And the switch is in 15 microseconds. Ah, that's the problem. That should not be milliseconds, it should be microseconds, guys. That should not be milliseconds. In the problem there, it should be microseconds because they have a set answer sheet here, and it only works if you use that as not milli but as micro. This here should not be milli, it should be micro. Okay. Now, if you use it as micro, the same thing applies. The only thing is here your required, your Req, your equivalent resistance, if you were to work it out, let me just get this. The answer here then will be 1290 as I worked out earlier. This thing here, because I didn't think they have a symbol for micro, but this should not be milli, it should be micro. So the equivalent resistance, if you were to work it out again, the equivalent resistance, okay, if you were to work out the equivalent resistance, it would be, what's my formula again? Equivalent resistance will be the inductance divided by the time constant. So Req would be inductance. Nothing has changed, only the time constant is just now in, the time constant is not in milli but in micro. So it's 10 to the minus 6, 15 micro. It should be micro, but I used an M there, which is in this case denoting milli. That's why I was a bit confused for the moment. Okay, so the inductance then is 5 Henry, still 5 millihenry. Inductance is correct. The time constant should be in micro. Okay, and this will give you, that's minus 6, that's 3, that's 15, that's zero point 0.3 times 3. So it's zero point 0.3 times 10 to the 3, if I'm not mistaken. So 300 ohm, 300 ohm. And you then use this equivalent of 300 ohm to work out the that equivalent resistance is equal to 1 over R plus 1 over 450, and that will be 1 over 300, 1 over R plus 1 over 450 gives you that R is equal to 1290 ohm. Okay, that is what R is. And let's go check if that is indeed the case. Okay, this problem only gets the correct answer. This 1.29 kilo ohm, which is 1290 ohm, if and only if the time constant is in microseconds, not in milliseconds. Okay, now they want to know in part B, or in B, they want to know what is the current in the inductor the instant the switch is thrown to position B. So let's say that we now flip the switch to position B. What is the current the moment that's that instant, the moment the switch is at point B? Okay, now the current, instantaneous current, is equal to the voltage drop over the equivalent resistance. Now you've already worked out the equivalent resistance. Okay, or rather you can write this in terms of what you just did, but you've already worked out the equivalent resistance. So voltage drop is, remember I just worked out the equivalent resistance to be 300 ohm, if I'm not mistaken. And then the voltage is 24, not 25, 24 volts. So 2 car batteries, 24 volts. So 24 divided by 300, let's check. 24 divided by 300, 0.08. So it's 0.08 amperes. Now here's the kicker, okay? Because I rounded earlier on, remember, when I calculated let me just see. When I calculate the equivalent resistance, okay, when I divide it, it should not be zero point 0.3 on the dot, okay? It should be 0.33. Let me just show you. 5 divided by 15. I rounded. Ugh, terrible. Clear that. 5 divided by 15 is 0.333. So the equivalent resistance should then be not 300 as I said, but 333. So if you plug in 333 here, 333, you should get, you see, equivalent resistance is 333, 333, 24 volts divided by 333 ohm, you get, let's check, 24 divided by 333, 0.072. Earlier on, I just rounded off. Okay, as long as you just know how to do the problem. Okay, so 0.072. Let's check. So if it's at point B, it is 72 milliamps. And let's check that. It's amps. Correct answer is 72 milliamps and 1.2 kilo ohm. Okay, just remember there I rounded. Then question 4. Okay, a coaxial cable has twice the length. Okay, so twice the length. But first, it's twice the radius of the inner solid conductor, and twice the radius of the outer cylindrical conducting shell of coaxial cable B. Okay, what is the ratio of the inductance of cable A to that of cable B? Okay, so cable A, coaxial cable A, has twice the length, twice the radius. So first of all, we need to understand what is the relationship between inductance and length. Okay, this is the relationship between inductance, and you need to know this because you're going to have to deal with a lot of coaxial cables where current flows in one way in this direction and in the other way in the shell. Okay, so inductance is mu naught, which is the permeability of free space, over 2 pi multiplied by the ln, or the natural logarithm, of B over A. And I'll explain now what B is and A is. B is the radius of the outer conductor, and A is the radius of inner conductor. Conductor. Okay, so there we have that inductance is equal to mu naught, the permeability of free space, divided by 2 pi times the natural logarithm of the radius of the outer conductor divided by the radius of the inner conductor. Okay. Now let's say the radius or the length of cable B is LB. The length of cable B is LB, and the radius of cable A, the inner radius of cable B is AB, and the outer radius of cable B is BB. Okay. This is for a single cable. Okay, this formula works for a single cable. This is the length of that cable, the radius of the inner cable, and the radius of the outer conductor. Okay, so now the problem states that, or rather, the problem states that cable A, let's say cable A, the length of cable A is equal to twice the length of cable B. Okay? So the length of cable A is twice the length of cable B, and that cable A has twice the inner radius of the inner conductor. Okay, so the radius, the radius of the inner conductor is twice the radius of the outer conducting shell. Okay, so the radius BA, what I said, B is equal to the radius of the outer conductor. Okay, so the radius of the outer conductor is 2 times the radius of the inner conductor of cable A. Okay, now we have these two relationships and we have the big formula. So for cable B, let's just do for cable B, we have that the formula should be, so for cable, let me just erase that. So for cable B, if we use everything we've been given so far, so for cable B, we have that the inductance of B is equal to, we have mu naught over 2 pi, we said before, multiplied by, and I forgot to include the length in the original formula, it should be multiplied by the length of that cable B multiplied by ln of the outer radius of B divided by inner radius of B. Let me rather keep it capital letters. B, outer radius of cable B divided by inner radius of cable B. Okay. You can write the exact same thing as for cable A. So for cable A, the inductance of cable A then is, the inductance of A is equal to mu naught. In the original formula, I forgot to include the length. We should multiply by the length of the cable. A divided by 2 pi times mu naught times the ln of the outer radius of A divided by the inner radius of cable A. So there we have these two formulas. Okay, this formula relates the length, the inductance to the length and the radii of this cable, the inner and outer radii of these cables. So we've already established that the following. We've already established the following. Let me just check. Where did I write it down now? Where in my notes? Okay. BA is equal to 2B. Okay. They tell us there that cable A, so let's just divide this by this. Now, what do we know? we know that for cable A, this is cable A. We know that for cable A, the length of cable A is twice the length of cable B. So we can write the length of cable A in terms of cable B. Okay, so the length of cable A is twice the length of cable B. They tell us that cable A has twice the length of of cable B. So we can write this as cable B and just say 2 times the length of cable B. Okay, so 2LB is equal to LA. Okay, and they also tell us that, remember already I also told you guys earlier on that they tell us that cable A also has twice the radius of the inner solid conductor and twice the radius of the outer solid coaxial conductor. Okay, so therefore this will be B. If you make that B, it has twice that. A has twice that of B. 2 divided by 2 just cancel, so it's just BB over AB, and this is just 2LB. Now if we were to write that out, if we were to divide this by that, if we were to divide cable A, cable A inductance by the inductance of cable B, if you were to write them on top of each other, this would cancel, that would cancel, 2 pi would cancel, 2 pi would cancel, mu naught would cancel, mu naught would cancel. Ln of ABB over AB and ln of BB, that would cancel, leaving us 2 over 1. So the answer would be 2 over 1, which is just 2. Okay, so the ratio is just 2. At least that is how I understood it. Okay, so if you were to do that calculation, you'd find that the answer is the ratio of the two inductances of these two cables is just 2. And let's check if 2 is the answer. Yes, 2 is indeed the correct answer, is 2. Number 5, quick and easy. That figure shows an LR circuit, an inductor, and a resistor, and with a switch and a 240 volt battery. Okay, so there we have a circuit, a switch, a 240 volt battery, a 10 kilo ohm resistor. Now, at the instant the switch is closed, the current in that circuit and the potential difference between A and B is what? So we need to calculate the current in that circuit when they close the circuit, and then we also need to calculate the potential difference in that circuit. Okay. First of all, now before the switch is closed, when the switch is open, uh, when the switch is open, the current is 0. It's 0 amperes. Now, the instant that they close that switch, the inductor resists any sudden change in the current. Okay, so inductor will resist any sudden change in the current. And since the current was 0 just before the switch was closed, it must also be 0 the moment after the switch is closed, because that's the function. That's what this conductor will do, or inductor rather. It will oppose that change in the current. Okay, so the current right after the switch is closed. So like the second they close it, okay, at that point the current is at time 0. The current I is also equal to 0 amperes. Okay, so the current is 0 amperes after the circuit is enclosed. Okay, because it was just before the circuit was closed, the current was 0, and the inductor will oppose any change in that current. Now, let's calculate VAB, the potential difference between points A and B. VAB. Now, the total voltage in this case, before I can get to that, that is what we have to calculate, but the total voltage is that of the battery, and it is equal to or it will rather it will be the sum of the voltage from the resistor plus the voltage of the inductor. They will must equal the voltage of the battery. Now the voltage across the resistor is just I times R for the resistor, the current that flows through the resistor. So it will be the current that flows through the resistor, 0 amperes, or let me just say 0, multiplied by the resistance. In this case, it is 10 kilo ohm. So 10 times 10 to the 3, that's the voltage across the resistor, plus the voltage across the inductor. How do we calculate the voltage in the inductor? How do we calculate the voltage across the inductor? That is what we want. We want the voltage across the inductor because the inductor is between points A and B. And the voltage of the battery, that is 240 volts. So the voltage across the inductor, by the way, the voltage across the inductor then is equal to 240 minus 0. So the voltage across the inductor is 240 volts. Okay? But the voltage across the inductor is also the voltage difference between points A and B. Okay, so the current is 0 amperes and the voltage is 240. So the current is 0 amperes, so it can only be one of these three, and the voltage is 240, positive 240. So let's check. And yes, the current is 0 amperes and the voltage is 240. Second to last question. Let me see. 6. This is a very easy one. This is a primary school question. Okay, so the switch in that figure is closed at time t, 0. The current I is 0. When the current is 15 milliamps, what is the potential difference across the inductor? So there we have the inductor, we have the resistor, we have 240 volts. The circuit is closed. Remember, the total voltage, the voltage of the battery, like in the previous question, the voltage in the battery should be equal to the sum of the voltage across the inductor plus the voltage across the resistor. Now the voltage, what do we want here? We want the voltage across the inductor. Okay, so we want VL. What is VR? What is the voltage drop across the resistor? That is just I times R. Okay, so the current, which in this case, they tell us is 15 milliamps. So 15 times 10 to the negative 3 multiplied by what is the resistance? 4 kilo ohm, 10 to the 3. So the voltage of the battery is 240 volt. So 240 volt is equal to the voltage in the inductor plus 15 times 3, that is negative 15 times 4, that's 60 volts. The voltage drop across the resistor is 60. So the voltage across the inductor is 240 minus 60, which is 180 volts. Let's check if there's 180. Yep, there it is. And wonderful, it is correct, 180 volts. Last question. And I like this one. So we have, what is the inductance of a series RL circuit, so a resistance and inductor circuit, in which the resistance is 1 kilo ohm if the current increases to 1/3 of its final value in 30 microseconds. Here we have the symbol for micro. Okay. So we know that the time constant, this is 7 by the way, problem number 7. We know that the time constant is equal to the inductance divided by the resistor. We saw this formula earlier. Okay. Now, we also have, or we should know that the formula, the current changes with time according to the formula. The final current, E final, that is the current in terms of T. E final is equal to 1 minus, because it is depleting, minus T over the time constant. How much time? And they want to know what would be, what's the inductance if the current increases to 1/3 or of its final value. Okay, so we know that T is equal to 30 microseconds. So the current in terms of T is equal to 1/3 of its final value. One third of its final current. So it's 1/3 of its final current. What would be the inductance if it's 1/3 of its final current? And 1/3 of its final current can be calculated using the formula, the final current, the formula we wrote down above, 1 minus e to the negative t over that time constant. So if we divide, remember this is 1/3, if it's 1/3 of its final current, so this function here should be, actually should be equal to a third. Okay, because it should be 1/3 of its final current. So if we divide on both sides here, remember this is just a formula. This we can actually leave out. That we don't have to write. I just wanted to write so you see where it comes from. The answer should be 1/3 of its final current if we use the formula like that. So if we divide, I final cancels in both. It means this 1 minus e to the negative t over the time constant should be equal to a third. Okay, so that should be equal to a third. Let me rewrite it. 1/3 should be equal to 1 minus, and some of you may have noticed now where I'm going with this. You then just solve for the time constant. Okay, so it is 1 minus a third. 1 minus a third should therefore be equal to negative e to the negative t over the time constant. Both of them are going to be negative, so you can actually get rid of the negative on both sides. So it will just be, rather it will be 1 minus a third. Oh, I switched them around here. This one here should be positive that and minus 1. Okay, so if we write them this way up, it should be 1t over the time constant. We divide on both sides by a negative. That will give us 1 minus a third. Okay, there we have it. So this should be 2/3, and this should be e to the negative t of the time constant divided by the time constant. Now, how do we get rid of that? How do we get rid of Euler's number, the exponent? Okay, we learn on both sides. So this will be t divided by the time constant left over, and that will be the ln of 2 over 3. Okay, if you remember your basic math, uh, we want the time constant, remember, we have the time. So the time constant, therefore, is equal to the negative of t divided by the ln of 2 over 3. Basic algebra, what is the time that they give us? They want it after 30 microseconds, so it's 30, oh, let me rather write it this way, 30 microseconds, or 30 times 10 to the negative 6 seconds, divided by the ln of 2 over 3, which is a constant. So the answer will be in seconds, which is what we want. The time constant is in seconds. And it is approximately 74,08 times 10. 74,08 times 10 to the negative 6 seconds. And so there we have. Oh, I just see the chat now. Mr. Nati asked, where does 33 come from? 33 is uh, from the previous question. I'll show you now. Let me just complete this one. So we have the time constant, but we want the inductance. So we have the time constant. And how do we calculate inductance from time constant? Inductance is equal to the time constant multiplied by the resistance. Now the time constant is 74,08 times 10 to the negative 6 multiplied by the resistance, in this case 1 kilo ohm, so 1 times 10 to the 3 ohm, and that should give you an inductance finally. If you were to multiply those two, you should get an inductance of 74,08 micro Henry. 74,08 micro Henry. Okay, I'm sorry I did not see that question there. Let me just finish with this one. 74 micro Henry. Or is it micro? Let me just check. Micro, yes. It should not be M there. That should be micro. 74 micro Henry, not milli Henry. 74 micro Henry. Okay, now back to that question earlier on. I got 33 because I wrote down the wrong. I rounded earlier on. What was the problem? It was the problem regarding, is it this one? No. Is it this one? No. No. It's here. Oh, the equivalent resistance. Okay. The equivalent resistance. When I worked it out, where did I get 333? Equivalent resistance. First of all, we needed to calculate the value of R. Okay, so equivalent resistance, R equivalent, equal to L, the inductance, divided by the time constant. Now I said here, this should not be milli, it should have been micro. Okay, so the time constant should be micro, so it's 15 times 10 to the negative 6, and this should be 5 times 10 to the negative 3 seconds. Henries, and this should be in seconds. Now if you divide these two, you get 0.3333 repetitively. Okay, it's 1/3. Now what I did here, the student asked the question, why do I get, why did I get, where does the 3 come from? Okay, this is where that 3 comes from. The equivalent resistance is 1/3. Okay, 1/3. just see, it is, yes, it is the inductance divided by the time should give you 0.333 equivalent resistance. Now, this is where the 0.333 comes from. Okay. So, going on, we now have the equivalent resistance. We want to find the current. And that is equal to delta V over R equivalent. Just to make sure something here. Yes. Oh, this should not be 0.333. This is why I'm checking. It should just be there. This one should become positive. If you divide this on your calculator, you'll get 333 ohm as the value. That's why I got that 3334. Originally I did it, but I rounded down to just 300 because I was doing it out of my head. But the C point should be the correct one, 333 ohm. Now if you calculate the current, it should then be voltage over resistance, and the voltage is 224 rather, divided by the current 333, and it should be point 0.7, is it 0.072? 0.072. That's 72 milliamps, and that is how I got that answer. And that is all the time I have for today. I hope you understood what I did. If you do not, just rewatch the video, and I see someone has already recorded it as well. Thank you for watching and have a great weekend.